from machine learning perspective. We are very happy to have you, Ritvik, and we are excited to learn about the ResNet paper with you today, and also generally how to learn machine learning papers in good effective. Thanks once again for joining. Over to you.
Right. Thank you. It's a pleasure to be here, and thank you for the kind words. But yeah, I see that screen sharing has now been turned on. Let me know if you can see my screen.
It's visible.
Cool. Just a second. Right. So, hello and welcome. This is going to be, as mentioned, a paper reading club where we are going to be focusing on deep residual learning, and they have been affectionately nicknamed ResNets. The purpose of this is to break down the paper to you in simple chunks so that it's easier for you to understand the paper once you go through it. Be assured that you have to go through it if you need to understand it, or you need to catch the things that are going to be presented here today, because this session is going to be what, 1.5 hours long or 1 hour long, and that wouldn't be enough for you to have the entire intuition behind ResNets. So with that, as mentioned, I have also been tasked with telling you briefly about how to read research papers and how to grab intuitions for them. I will touch upon that later and expand on this slide when I reach the end of this session, which is going to be about primarily ResNets and how effective they are in 2023, because ResNet or Decoding Deep Residual Learning is a paper that came out in 2015. So it's a foundational paper in the deep learning community, and it introduced something called ResNets, which is an architecture that uses deep residual learning for image recognition. And then, of course, ResNets paved the way for much more and much deeper research in the deep learning community. So with that, let's get started into what a sort of TLDR of what the paper is all about. So normally, as you add more layers to a deep learning model, it should get better. That's the idea. And it's, by better, we mean that it gets better at doing the task which it is meant to be doing. But in practice, deeper networks often do not perform like that. They can be harder to train.
Those who are not have any doubt, please go on mute. Sorry, but you can continue.
Yeah, so they do not perform. May I go ahead?
Yeah, I have muted the person. You can go ahead.
Good. So as I was saying, they do not perform as expected, and they can be harder to train because of something called vanishing and exploding gradients, which we will talk about later. But to address this problem, what the researchers did, and this came out from Microsoft's lab. Kai-Ming He was a lead there then. And to address this problem, they introduced a simple and groundbreaking idea. Instead of trying to learn an underlying function directly, which is what deep learning is all about, it's about learning the underlying function directly. They wanted to propose, or they proposed something about learning the residual, or just the gap between two network modules. And the way they phrase this is that learning an underlying function directly, or the residual between the current layer or the output of, or the desired output, will give them a better and faster way to train the networks. This is done using something called shortcuts or skip connections. And what these shortcuts do is that they bypass one or more of these layers and directly add the value to the next node. So, like, imagine for a second that you're trying to solve a math problem, and instead of calculating the answer from scratch, you use a previous problem's answer and just figure out the difference between the old problem and the new problem. This difference, or the amount that you needed to figure out, was the residual. And ResNets use these residual connections to effectively skip layers, making it possible to train, very hugely deep neural networks, as deep as 152 layers. Of course, we went deeper than that, and we even trained 200 or 300 layers after that. But at the time, and you have to understand that this paper came out in 2015. So at that time, 152 layers was a huge thing, huge amount of parameters to train without having vanishing gradient problems. So when tested, they of course had to publish a paper for this, and they had to test the ResNet architecture, and they found that it actually improves training and the loss decreases rapidly. But what actually is the problem that is being solved here? So the paper in question aims to ask a central thing. In terms of deep neural networks, is deeper always better? And what that essentially translates to is, if we stack more layers, is it always going to help us? So I have an analogy here, and I want you to kind of pay attention to this analogy, because this analogy is going to be the story that hooks you to the ResNet paper. So think of training a deep neural network like trying to pass a whispered message in a game of telephone. And I'm sure most of us have done this in our school days, or some of us might even be still doing this to this day. So we keep a string of friends in a line or in whatever structure we might prefer, and then we whisper something in their ears, and at the end we ask the person, what did you hear? And usually they come up with something gibberish, and we have a nice laugh. So I want you to imagine this this situation for a moment. And to make it more interesting, the first person whispers a puzzle, and the group of friends are progressively smarter. So each friend is progressively smarter than the previous friend, sort of like a layer in a deep neural network is progressively, extracting deeper features than the previous layer. And each progressively smarter friend tries to decode the puzzle. So usually what would happen is, as we go through the line of friends, the original message will be lost, and the last person will not be able to figure out the message. But the catch here is, of course, the more friends, and in deep learning terms, the more layers you add to the line, the harder it gets to keep the original message intact. So if we add maybe 200 friends, if we have them, at the very end, the person who is going to hear the message will not even probably have a semblance of what the original sentence was. And unfortunately, in the present day and age that we live in, a game is not considered a formal framework for studying anything. So we must once again resort to mathematics. And in maths term, let's say F, or capital F, is the class of all functions with weights and parameters. So, deep learning is famously all about approximating a function. So let's just say that the function that we want to approximate is small f over here. And capital F is the class of all functions that are possible. So which means that for all functions small f, there exists a set of parameters or a set of weights and biases that can be obtained through training. So if you tune your weights and biases, you will eventually be able to land at f, which is a small f, which is the function that you're trying to approximate. And that function can be something like whether it's a dog or a cat in an image, or whether you're say suppose trying to segment an image. So if you look at my screen, segment the foreground with the background, which is what Zoom is doing currently. All of these are just functions. And what we are essentially saying in the slide is that let's just assume that capital F is the set of all functions that are possible, with training a deep neural network. But what we can say here is that the expression of that function or the optimal function, which is f star, is argmin of the loss function given data and labels, which is x and y, and the function, of course, and provided that this function should exist in the class of all functions, right? And it can be hypothesized, or we can say this, that the more powerful the class of functions, or the bigger the class of functions, the better it will be at approximating the optimal function, which is f star. And if you ever get confused, or if you are not getting something here right now, please stop me and ask, because this is something which is central to understanding how residual networks work. So again, f star is a function that you're trying to approximate. What are you trying to approximate? It might be something like, it is exactly what you're trying to do, or the task you're trying to accomplish. So if you're using deep neural networks to predict the next word, then f star is the optimal function which will allow you to predict the next word given data and labels. But if you're using your deep neural network to predict whether I am a human being or an alien or Elon Musk, then f star is that optimal function which will predict the probability that I am a human being, which I hope I am. But yeah, so that's exactly what is happening here. But what is capital F? Capital F, or capital F bar, which is shown in the slide here, is the set of classes, or a class of functions. Like, it can have multiple small f's, like f star, f naught, f1, f2, f3, whatever. And within that class of functions, it is supposed to find the f star, which is the optimal function. And that is exactly what the training procedure will be. And as I was saying, it can be hypothesized that the more powerful the class of function is, so the bigger the capital F is, it will let us approximate f star better, because like that's what our end goal is. And what we can do is, with training, we aim to find more and more powerful f bar that will eventually approximate f star. So what we are trying to do here in the slide is that we are I hope my pointer is visible. So this is the f bar that we begin with, and then we move just a second. Yeah, this is the f bar that we begin with, f1 bar, and then we move progressively deeper. So what we are trying to do is we are trying to train the neural network, and we are trying to grow the class of functions. So by growing the class of functions, we are actually growing their size. So the number of probable f stars that might be possible within these f bars are growing. And that's exactly what we are trying to do with training. Now, what happens is, since f2 bar is not exactly the same class as f1 bar, it doesn't contain f1 bar in its entirety. What is happening is that it is progressively growing bigger in size, but it is not growing in the direction of f star, which is what we want to approximate, which is our optimal function. So what it essentially means that including with f bar growing in size, not including the first class of functions, which is f1 bar, there is always a probability that f bar might not be approximating f star at all. It might happen like through backpropagation and through the tuning of parameters, that f1 bar and f2 bar just grew in this direction. But it might also happen that it does not. So how do we mitigate that problem? And the one way to mitigate that is nesting the class of functions. So the solution is to nest the function classes as we go forward. In other words, this means the progressive function classes must contain the original function class in some respect. So f1 bar is contained within f2 bar, and f3 bar is contained within f4 bar. And thus, as you see that it's generally growing like a shell in size, we are encompassing all possible functions inside that class of functions. And the probability that the optimal function that we are trying to approximate with our weights and biases and our training data and label will be eventually encompassed within a bigger F bar, which is our class of functions. And that's the math part of it. And if you have trouble, tying that back to the analogy of friends whispering, what it basically means is that it's basically making sure that some of the friends in the string of friends occasionally hear the original puzzle. So say suppose I'm whispering the original puzzle to the first friend that I have, and they're whispering to the next friend, and they're whispering to the next friend, and they are all whispering gibberish at the end. But what is happening is that the original message is being replayed to say nth friend in the row. And that ensures that whatever is lost in translation while we are whispering, the nth friend is actually getting the fresh information again. So they are propagating that. Okay, and that's exactly what we aim to do with nested function classes. In the context of the paper, because we want to understand how the paper has presented that, in the context of the paper, they're suggesting that when training deep neural networks, instead of trying to learn a complex function directly, which is trying to approximate F star directly, it's sometimes easier to learn the difference or residual between the input and output. This is achieved using shortcut connections that skip certain layers. So going back to here, we can see that we are skipping certain friends and adding the original puzzle to certain other friends. And
sorry to interrupt. There is one question regarding the F1, F2, F3. Can
cool.
you have a look? The messages.
Sure.
Just that it provide more clarity to them.
Sure. Can you just repeat the message? I'm having trouble.
Can I say F1, F2, F3 are same equation / function with different weights? Can we consider it like that?
Okay. Coming back to this slide, what we kind of need to drill down here is that small f is the function. Capital F, in whatever form it is being presented here, F bar, F1, F2, is the set of functions. Okay. And you're right partially, because F star, so let's say that we have small f1, small f2, small f3 within a set, and we are calling that set capital F, right? And small f1, small f2, small f3 are all the same equations, but with different weights. And you're right with that. But what we are trying to do is we are trying to grow the set of functions, progressively. So that when we grow the set of functions progressively, what happens is that our probability of finding F star within small f star within F1, F2, F3 grows in probability. Does that answer your question? Does that make sense?
Vinod, I hope your question is answered. Yes, you can go ahead. Thanks
Cool.
for the answer.
Absolutely. So as I was saying, what we want to do here is just add the original information periodically to our group of friends, and that is exactly what the paper is suggesting that we do. This is achieved using shortcut connections, which means they skip certain layers and add that information to certain layers. And these connections help the learning process easier without adding extra complexity, because you're just adding the original plus you're just adding the original information after a couple of layers. You're not really multiplying something, or you're not really doing some computation so that your complexity increases. And what it looks like is kind of this. We have our weight layers, and we have our activation map, or activation layer, or ReLU. And this is okay. So this is where we are starting from. This is our X, or our original information in the story, or in the analogy that we were talking about. It is our it is our original puzzle. And this is the function. Okay, so this is our group of friends, and in it we are going through the weights and biases, and we are passing ReLU or our activations through them, and this is how generally it should look like. But what the researchers have done is that they have taken X out of this and they have kind of added it back here. So the resultant network is fx plus x with an added identity, which is of course x. And what what they are proposing is that this is kind of helping the network learn better. So what exactly is the solution, and how do the authors propose that this solution makes the network learn better? Firstly, they propose the solution to be something called deep residual learning. And here is where we need to kind of focus down and understand what exactly they are proposing and how is it so beneficial to learning. The original problem the original learning problem is to train a neural network to approximate a function hx. Okay, and this is the function. Let's just say this is x, and this is going through weights, and this is going through an activation function, and then through weights again, and it is being passed on. And usually at the end, there's a softmax layer or a layer which decides whether you have correctly predicted from the training or not. You match that prediction with the target, you arrive at an error, and you pass that error back. So you backpropagate and you tune the weights and biases, right? This is what deep learning is all about. And we all know this. This is Bible knowledge to us at this point. But what is happening here is that we are saying that the original problem, let's say that the network or the architecture that this entire thing is called hx. And deep residual learning reformulates this problem by letting the neural network approximate a residual function, which is hx minus x. So we are saying that, okay, what we are going to do is we are going to take x from here and we are going to add it back after it goes through all the weights and activation functions. And what that essentially allows us to do is say that this new network architecture can be called fx, because of course this is not the same thing as this. It has changed. We are adding x back here. So now what is hx? Well, it's simple, because we are adding, x to here. Hx is fx plus x, right? So can people tell me in the chat what fx is? If the host, can you please tell me if someone gives an answer in the chat?
Yeah, sure. There is a question meanwhile. So the sure. fx plus x, what does the plus means over here? Is it sum or concatenate?
Okay, is it sum or concatenate? Cool, that's a good answer, but it's sum. Okay, at this point, we are just trying to understand how this network architecture is working. Okay, and we just want to see that how exactly can we reformulate the problem statement with this network architecture that is present here. Any answers?
Okay, f is a class of functions. That is one of the answers. Okay, no. What we see, I'm going to be reading this out again. hx is the network that we have here on the left of the screen. Okay, and what is that network? It is trying to, it is the deep neural network that you are using, and x is being passed through these weights and biases, and you're using x or your data to predict certain things in your data distribution. Okay, and this network architecture is called hx. Now we are modifying this network architecture on the right of the screen, and we are saying hx is now fx plus x, and fx is this entire thing, this network architecture plus this shortcut connection. So hx is now fx plus x. So then what is fx? Here there is one answer where f is the feed-forward neural network. F is like f1, f2, or f3. Okay, that's not
That's not the answer I was
Another
looking for.
answer is fx is an activation function of x.
You're thinking in the right direction, but you're thinking too deep. Okay, fx is not the activation function. Activation function is this one. It's written. Okay. If I say hx equal to fx plus x, and if I say what is fx, you can just say hx minus x, because that's a simple answer that's staring at us from the screen, right? So if we want to say what is fx in this network architecture, we can simply say that it is hx minus x. Okay, and hx is this original network architecture minus x. Okay, this is what we kind of need to do. We just need to see the equation in its form and substitute the values and see, okay, where am I, or how can I reformulate hx? So fx is equals, I'm sure, I hope you can understand from here, fx equals hx minus x. So this is equivalent to approximating hx in this, but it can be easier because we are not really trying to approximate hx. We are not really trying to approximate a function without having any knowledge about it. We're really trying to approximate hx, hx minus x. We are trying to approximate this part of the network, and this part of the network, which is fx, can be called hx minus x. So we are trying to learn the difference. We are trying to learn the residual, and that's why it's called residual learning. And please tell me if this is not clear right now. Bombard me in the chat, because this is really the stepping stone to moving forward. I am looking at the chat. Someone says, in case we may lose any details at any step x, then we may add x to fx, which is true in essence. In case we lose any information back, we are adding it. We are adding a shortcut so that it is able to retain those informations. But what I really hope that you take from here is that what is residual and what is residual learning, because Deep Residual Learning is the name of the paper, and Deep Residual Learning is what the authors are trying to achieve here. So what is residual here? Residual is this network, okay? This part of the network, just this part, not the shortcut, not the addition. It is called fx. And how can we mathematically write fx from this equation? We can say that fx equals hx minus x. And since we are subtracting the original information from the representation or the function hx at this point, what we are essentially doing is learning that gap or learning that residual. What is that residual? This part of the architecture. I hope that it's clear, because I do not see any messages, or it might be acting up on my end. So in a real world, shall I say predicted word plus actual word? We are a bit far away from the real world. We are in the pen and paper world, where we are just trying to understand what the network architecture is. If it is a little bit bloody, I promise you it will make sense as we go through it. But in the real world, how residuals work is something which is yet to be seen. fx is the residual? Absolutely it is. Okay, moving on. So what someone says, someone said, I think there's a plane in the background. If someone can mute themselves, that would be great. What someone said in the chat was that, if there's a loss, we can always add the original information or x back, so that the loss or the loss in translation is kind of brought down. And the fancy way of saying this, this entire thing is called the degradation problem. And the degradation problem is like exactly how you described it. If there's a loss in translation, if our friends, after listening to the whispers, tell us gibberish, then it's a degradation problem. The degradation problem is a phenomena where the training error of the deep neural network increases as the network becomes deeper. Okay, so this is because it becomes more difficult for the network to learn identity mappings. What is identity mapping? It's a fancy way of saying that it is not being able to understand or retain the original information from the start of the training process. So, which is not ideal if it's not able to understand or retain back the original information, and it's progressively, extracting features at each layer, it is possibly doing a very bad job. So deep residual learning can help us solve this degradation problem. And the next part of the solution is called identity mapping, because they want to understand what identity mapping is and how it helps deep residual learning. So the authors present the residual learning block, which consists of two parts. The residual function, which we are all on the same page now. Fx is the residual function, which is a stack of layers. So this is a stack of layers which learns the residual between the input x, this is the input x, and the desired output. Okay, and the shortcut connection. So this is the shortcut connection. The shortcut connection actually adds the input x to the output of the residual function. And the shortcut connection is important. So we kind of understand how the shortcut connection works, but the shortcut connection is important because it allows the residual learning building block. So this is the entire residual learning building block to learn identity mappings. Okay, it is, whenever you think of these jargons, identity mappings, residual things, always think back to the analogy or to the story. Okay, what is identity mapping? It is just the original puzzle being repeated back periodically to our string of friends. So an identity mapping is a function, in fancy terms, it is a function that simply returns its input. So if we are passing x is going, that is identity mapping. Okay, identity mappings are ideal for the first few layers of a deep neural network because they do not change the input data. So what this means is that if we have, so these are the two parts of deep residual learning, right? One is a residual function, which consists of the weights and biases and the activation maps, and those need to be tuned, and the residual function needs to be learned. And that's just this part, the part that I've highlighted in the left of the screen. The other part is a shortcut connection, which is X. Okay, and they said that both of these things are required because we need to add the original information back, or we need to add X back to the network periodically. But we also need to approximate the function, or we also need to, learn or make the FX learn from these weights and biases. Okay, and that's how the network architecture is going to go forward. So let's take a look at the architecture. Okay, and I am not going to be drawing on the screen or presenting a sketch as I've done before, because that would defeat the purpose. Let's take a look at the architecture as the authors have presented. So the plane network, is this visible?
It is slightly blurry, but it's understandable.
Cool. On the left, on the very left, is the plane network, which is inspired by the philosophy of VGG nets, which came back before residual ResNets. Okay, it has convolutional layers, mostly with 3x3 filters, and follows two simple design rules. For the same output feature map size, the layers have the same number of filters. If the feature map size is halved, the number of filters is doubled, so as to preserve the time complexity per layer. And just, if you do not want to pay attention to exactly what the intricacies of the architecture are, that's completely fine, because you can always reference a blog or a paper or something else to understand what those intricacies are. But on the middle, we have the proposed plane network, which is 152 layer deep, and which has a string of weights. It has a string of activation maps, pooling, and such other operations. And what is being done on the very right, which is the proposed network architecture, is adding the original identity map at each stage, or adding X back periodically. Okay, so what changes have the author proposed is simply adding X back periodically. Okay, and if you have to sort of take away anything from this network architecture diagram, what you kind of need to remember is that they haven't really done much or many changes to the entire architecture. They have periodically added something back. And it's not even something that's really complicated to understand. It's just the original information, or the information at that stage. Okay. And the code for this residual block is actually pretty straightforward. I am a TensorFlow or Keras guy, and therefore I wrote it in TensorFlow, or I kind of took inspiration from d2l.ai, which is the website where you will be finding much of the literature here. But this is really simple to understand, and if you are coding deep neural networks, or if you are in deep learning, you will be able to understand this pretty easily. But if you are feeling overwhelmed with this, I just want you to focus on the yellow highlight of the page. And if you can see that it's basically checking, if a part of the network architecture is a convolutional layer or not, and then it's just adding X back at that stage. And that's it. That's the main, driving logic of this code. And I'm sure you will be able to, take a screenshot of this, or, reference this later when you go through the recording. But what I really, encourage you to do is try to implement a deep neural network, try to, throw in residuals at certain stages, and see how it goes. Okay. I see someone unmuting. Is there a question? Right. And that must be me who is mistaken. If there's a question, please put it in chat. I request the host to let me know if there's a question, because I'm not really able to access the chat. So moving on, because we kind of understand what ResNet says. Okay, it seemed a little bit daunting and complex at first, but it's just adding X, or adding the information at a stage in the layer periodically through the network architecture. And it came out in 2015. So why is it still so relevant? Like, why do we still need to learn about ResNets, or why are residual connections still used? Because at the pace at which machine learning is progressing, there is new research coming out every day. So why are ResNets still here? And I want you to really look closely at the Desmos graph created on the screen. So fx is a black line on the screen, which is tan h of x. And you would know this if you have gone through any deep learning books or courses or whatever. One of the activation functions that is famously used is tan h. So g of x is the derivative of tan h of x. Okay. And that's the blue line that you see on screen. And h of x is the derivative of that, of g of x. And we are just raising that to a power, because let's just say that power k is our weights and biases. And something very interesting happened when we kind of tune k. If we bring down k, we are seeing that it is exploding, like it is going through the roof and going to infinity. But if we kind of increase it, the values come back to 0. And this is something which is called vanishing gradients and exploding gradients. So when it goes to infinity, you guessed it, it's exploding. When it comes down to 0, it's vanishing. And so what is happening here is that basically it is because of chain rule. And what is chain rule? We know that dy of dz equals dz of dx, or dy of dx equals dx by dz times dz by du, and something like that. And we can always expand this into a format where we express y in terms of the original parameters. And what happens when we kind of do one derivative after one derivative after one derivative is that the derivatives in the denominator increase. And if the derivatives in the denominator, like multiplied in the denominator, have increased, and they are of a large amount, we know that the original value will tend to infinity. But if it kind of decreases, we know that it will essentially come down to zero. And what this means in deep neural network terms is that when we are backpropagating through the entire neural network architecture, and we are arriving at say a gradient of the loss with respect to the weights, if there are enough layers, that means there are enough weights. If there are enough weights that need to be tuned, that means that the derivative of the loss with the weights will sort of lead to a vanishing gradient problem. Why? Because dl, which is our loss, by dw, which is our weights, and dw will eventually expand into w1, w2, w3, w4, and as many weights as you have for as many layers as you have in your architecture. And if those layers are something like 152 or 200, you can understand why it's a problem. It will eventually lead to gradients coming down to zero. If gradients come down to zero, big thing. Why does it bother us? It bothers us because then we don't know how much we need to tune those weights so that the loss comes to zero. Okay, dl of dw is going to zero at certain stages of the architecture. What that means is that at certain stages of the architecture, we have blackout. We have no idea of how much we need to improve or how much the weights need to be tuned. Does this make sense? Can we have some yeses, nos, absolutely confused in the chat? Okay, I don't see any, which means that either people have given up at this point or people are really getting everything. And I really hope it's the latter one. So, sorry. In deep neural networks, vanishing gradient can occur because you multiply some small numbers together, like when you calculate gradients during backpropagation, and the result becomes smaller, leading to gradients that are too tiny to help network learn effectively. This happens.
There is one question is there in the chat. How does it affect other activation functions like sigmoid or ReLU?
Okay, other activation. So I assume that you are saying that tanh
instead of tanh, is there some other function replaced?
Yeah. See, the point is, even if you use any other tanh, because it's very easy to code up in Desmos, very beautifully gives us a tanh function. But ReLU is something that you can really easily write in Python. And what I encourage you to do is use Python, use NumPy, write ReLU, write the derivative of that ReLU, and you can do that with any SciPy or any other library. Okay, just write how to do derivative of a certain variable, and you will arrive at that. And keep doing that derivative in a for loop, and see, kind of plot those derivatives using matplotlib, and you will arrive mostly at the same same graph. Because what is happening is that even if you are using other activation functions, the activation function is not the driving force. What is the driving force is the derivative. And as you keep on doing the derivative, you'll only keep on doing the derivatives as long as you have more weights to tune. And more weights to tune only come if you have more layers. So if you have more layers, you'll have to keep on doing the derivative. and that will eventually lead to a vanishing gradient problem. And I encourage you to see and verify that by yourself using Python, or you can even use Desmos. In that case, you will not need to code anything up or write any code before you can see the vanishing gradient. But just go and see what the mathematical formulation of ReLU is. Write fx equal to that mathematical formulation and keep doing the derivative of that, and you'll arrive at the same kind of results. So hope that answered your question.
Thanks. And one more thing, K here is the weights, right? Number of weights.
Yeah, K. Think of
how would negative, like we have a range from negative to positive, right? How are we going negative in weights?
Yeah, see, this is something which is a very good question, because this is something that would be automatically bypassed if we used ReLU. But the idea was not to say that if we go to negative or we go to positive, then this will happen. The idea is to say that if you increase or decrease K, okay, then the vanishing gradient or the exploding gradient problem might happen. And in reality, in a neural network, it wouldn't even be this simple. Like we all know that the expression of a line is y equals mx plus c, and that's exactly what is happening inside of the first layer of a neural network. But then you have an activation, so y equals mx plus c, tan h of that, so tan h of y equals mx plus c. So you already have kind of an offset thing happening inside of this equation. What K will do is simply increase or decrease that. Okay, it's a power, or it's an expression tool that you can use to sort of increase or decrease the power of derivatives. Does that make sense?
Yeah, makes sense. Thank you.
Cool. Coming back. So the result becomes even smaller, leading to gradients that are too tiny to help the network learn effectively. Okay, and this happens especially in deeper layers of the neural network, and you already know why this is happening, because as you increase the layers, you increase the number of weights in the layers, you increase dl by dw, and therefore gradients are more likely to vanish. Skip connections, as we know by this time, also known as residual connections, helps address this problem. And how do they do that? They allow information to skip certain layers, right? And this is what is happening here. They allow information from X to skip these layers and be added directly here. So what you're doing is you're essentially bypassing the multiplication steps or the weights that cause the gradients to vanish, and you're adding that information back periodically. So it's like saying that dl by dw might come down to 0. We completely agree to that. But what if we just add epsilon to that? So dl by dw plus epsilon. And epsilon is a very small number, or in this case, it is x, which is the original information. And what is happening is that thus the gradients are not really dl by dw, or it's not simply the expression of delta change in loss with respect to delta change in weights. It is the expression is reformulated as delta change in loss by delta change in weights plus something. And that plus something is actually helping the backpropagation process, because now certain stages in the network architecture do not have complete blackout. They have some residual information left, and that will help the network learn faster as it grows deeper. In coming back to our analogy, when you use skip connections, the activations in the deeper layer get some extra input from shallower layers, which prevents them from becoming exponentially small. This is crucial when using activation functions like tan h or something else, which can make the vanishing gradient problem worse, as we have seen. And in the original puzzle, the original analogy, the puzzle is repeated every once in a while, and thus every friend on the string has an accurate picture of how much they have misheard. And what this means is that this person is saying the original puzzle, And that original puzzle is being repeated back to this person. Okay. And that original puzzle is being repeated back to this person and this person. So these people do not have that original puzzle, and they might have misheard something. They might have heard, gibberish. So at the end, when we are saying, okay, what did everyone hear? These people will give us the perfect information, right? But these people will give us some format of a gibberish. And they will then realize, okay, that means I might have heard this part wrong. So I need to tune myself and I will learn better. So these parts are actually learning because we are adding this information periodically. And think of these friends as layers. So these layers these layers have this information added periodically, right? But these layers at the end, their weights see that the loss is quite huge with respect to them. So they will then suffer from inferiority complex and say that, okay, the next layer is so perfect, but I am not. So I kind of need to tune myself better so that I can approximate the function, or I can, retain that information better. And thus the learning process gets easier. Please let me know if this doesn't make sense or if you want me to repeat this part. So in simpler terms, these skip connections, these connections help keep the gradient or the information alive and prevent it from becoming too small as it travels through the layer during backpropagation. And like all great architecture, ResNet has evolved. ResNext is a natural extension of the ResNet architecture. It introduces the concept of cardinality. Please keep in mind that this part that I'm saying is not actually part of the paper. These are later architectures that have come out, and I'm just letting you know these things, sort of familiarizing you with these things, so that when later on, if you study them or when you study them, it acts as a shortcut in your mind so that you get why ResNets have been so popular. So ResNext, as I was saying, is a natural extension of the original ResNet architecture. It introduces parallel pathways or branches within the residual block. So every residual block has parallel pathways. DenseNet, or short for densely connected neural networks, densely connected convolutional neural networks. Here, each layer receives input from all preceding layers. This results in a highly interconnected network. And wide ResNet, which is a variant of ResNet with the width of the network or the number of channels. So RGB has like height, width, and channels. Every image has height, width, and channels. So the channels are increased while the depth is decreased. And if this kind of is too much at this moment, please do not worry, because these will all make sense if you read ResNet and then you read the subsequent papers, which I highly encourage you to do so that you kind of cultivate your literature survey. ResNets have also been adopted. They have gone past CNNs, and many modern architectures have now adopted ResNets. The most notable is transformers, which is a popular architecture for natural language processing tasks and incorporates residual connections in their design. Each sublayer in a transformer, such as self-attention or feed-forward networks, has a residual connection. It has been vital in the growth of attention and models such as GPT that we now use. Augmix is a data augmentation technique. It blends certain other data augmentation techniques, and it's not a network architecture. It's sort of like a pre-training thing, but it uses residual architectures as well. So it's important there as well. Autoregressive models, such as some variants of transformers in NLP, can benefit from residual connections. These networks or these architectures kind of rely on residual connections to make them more efficient and more faster. Graph neural networks are designed to process data which is structured as graphs, and they too have some variants where residual connections are needed. So in short, residual connections have been super important in deep learning, and they're being used to this day. If you think that, okay, something came out in 2015, adding X back periodically, I don't need to really know that to understand how GPT works, right? You do. It is that important. And why is it important? I hope you understand kind of the kind of problems it solves, and how simply and effectively it solves it. So residual connections are so great. Why not sprinkle them everywhere? Okay, why not just have every block of deep learning be a residual block? And if there's something that I want you to think about, if when you have ended this session and when you go back to read this paper, is this: why not add residual connections everywhere? And I can sort of like give you a hint, but you have to go on this exploration journey and really answer this problem on your own. So every architecture is new and every problem has to be separately examined. But we have to remember two things. One is on the right, nested function. So nested function classes have a higher probability of containing the optimal function only and only if there are enough number of function classes. So if we stopped at F3, we wouldn't have approximated F star. So we need to have the network architecture deep enough for the nested function classes to have sort of approximate the optimal function. Okay, and this is something that you need to remember. So when you're designing shallow neural networks, which are not deep enough, or just a multi-layer perceptron, will residuals help you? Probably. But will it really help you, approximating the optimal function? Probably not. And second is residual learning. So residual learning is beneficial. So residual is this part of the network architecture. And what we are doing is we are learning this part. So residual learning is beneficial when the residual gives the network a higher advantage than optimizing the parameters. What this means is that if you just stack layers and if you don't add any shortcuts or any connections, and you evaluate the performance of that architecture at the end, if you see its loss, and then you add that X periodically and you see that loss, you have to see whether it's really going down or not. In some cases, it does. In CNNs, it does. It might so happen that you are designing your own neural network, which do not conform to the rules of CNNs or transformers or attention. Will it really help then? Okay. Will it give it will learning the residual or this part of the architecture be significantly more, helpful to you than just optimizing the weights and biases? And these are, things that you need to sort of think on your own when you're designing your own architectures. And third is adding too many shortcuts will force the network to learn X much better than the features it might discover. So if you add X periodically, what happens is that, you sort of arrive at a perfect representation of the data. You're trained perfectly on the data. You learn things from the data so well. But what if the data changes? What if the network hasn't really learned but memorized? What if by adding X periodically, we have just reinforced it into learning X better, and it has not really understood features? Which means that if I, if every day for the next 30 days, if I come and speak to you on a Zoom chat, you'll probably remember my face. But would you be probably able to recognize, me in some other attire or some other glasses or if I put on makeup or something like that? Probably not, because you have not really understood the features of my face. You've just memorized it. And that's something which is called overfitting. And we genuinely don't want that to happen to our network architecture. So some of the like answers that I might give you in general terms as to why not use residual connections everywhere. But the real answer has to be found out by you with pen and paper when you're trying to design or when you're trying to learn how your models will learn. And finally, coming back to the original slide that I started with. So this is about reading a research paper and understanding a research paper and going through a research paper at your own pace. And the reason why I'm smiling is because I still have problem to this day reading research papers and figuring out stuff from it. It is hard. It is an uphill battle. It is something that is not everyone's cup of tea. But if you are here, if you are listening to this, if you have, tried to answer my questions, listen to whatever I have said, it means that you have on a Saturday afternoon enough thirst to go into deep learning, to read research papers. So I salute you for that one. And I also know that you will do a great job reading papers and also implementing them. So first is finding a niche. There's about 20 or 30 papers coming out every day in machine learning. If you try to read all of them, I feel sorry for you. But it's not something that we should even attempt at doing. There's image models, there's vision models, there's large language models, there's reinforcement learning. You need to pick and find a niche that calls to you, that that inspires you, that motivates you to read the paper. Okay, that's the first thing. Or if you have a research problem that you're working on with someone and you need to read a certain type of paper, find that niche. Don't try to read every paper out there. Okay, teach what you read, even if it's to your 10-year-old brother or someone from your college or someone from your workplace or some of your friends through a ML paper reading club such as these. Teach what you read, and teaching will make you learn things better, because then you have a fear or have this subconscious thing that I don't want to teach something which is not right. I don't want to say something which is not right. I have to deliver the information correctly. So teach what you read. Use any and every tool at your disposal. Okay, copy paste a part of the paper, put it in ChatGPT, tell it to explain it to you in your terms. Copy paste a part of the paper, put it in Bard, tell it to show diagrams of that in as lucidly as possible. Go on YouTube and search with that research paper and ask in the comment box. Go to the mail and mail the original authors about something that you can't understand in the paper after, of course, you have read it a couple of times. And sometimes they also reply, which is a great thing for you. So use any and every tool at your disposal. If someone tells you, okay, yeah, I mean, ChatGPT is good, but you can't use it for serious academic research, that's not true. Okay, use it for explaining things, use it for use anything that you can find to explain it or to make it easier for you to understand, but also fact check it. If it says something, or if it throws a big paragraph out at you, which is probably not true, you need to sort of understand that paragraph and see how it correlates with the paper. If it doesn't, it's probably hallucinating, or that person on YouTube has probably not taught you the correct things. Okay, so always fact check. Even after you have listened to me blabber for I guess 1 hour now, I encourage you to read the paper tonight. Okay, when you go to sleep, take 1 hour for yourself and read the paper and see whether I have said the things that's written in the paper, or whether I've just made stuff up. Okay, always fact check things which you learn, but also use any and every tool at your disposal to learn. Create a working example. Okay, if you find a paper and if you find the code, there's a website called paperswithcode.com. Go onto that and check for the paper. You'll probably find the code. If not, you can wait for the code and the code will come. from the authors or from somewhere else. And I encourage you to pull up an collab notebook and sort of put that code in, try to get it to work. It won't work, you'll throw some error, you'll get frustrated, good. That's where you're learning. That's your loss function, and you need to tune your weights. So go through that process of creating a working example and coding it up, and that will let you understand the paper even better. Because once you code it up, you'll find that, okay, this needs a special layer here, this needs a feed forward network, but the authors haven't written about it, which is bad. But hey, I discovered something while implementing it. Okay, you can't just do this and this. You probably need to have an intermediate layer between them, and I learned a lot by doing that. So I really encourage you to do that. Document as you go, because all of this might take you weeks, it might take you months. If you do it correctly, it will take you years. You'll eventually love it, but you kind of need to have some form of documentation. One of the things that I was doing while preparing these slides was going back to my notebook that I used to learn deep learning from back in 2017-18. And in that notebook, I've written about ResNets, and I've written one, I could have shown it to you, but it's not here. I had written one line, and it said, it's about learning the gap. And learning the gap means learning the residual. And that helped me recollect every bit of intuition I had gathered while reading that paper back then. And that, coupled with everything that I've learned now after 2018 through these years, is what you're seeing on screen. So document as you go, not just for others or publishing as a blog or doing a YouTube video. Document because it will help you to learn, and it will help you to get better. And the last point is really the most toughest one. It's asking, why does this paper exist? And this might seem really redundant, because after reading a paper, when you ask yourself, why does the paper exist? The answer immediately comes to you. Oh, because it solves this and this problem, or this is a new architecture and it's so much better. But as you keep that question in your mind, and you sort of roll with that question for the next couple of days or weeks, you begin to ask yourselves, why this? Why not this? Why not something else? Why not a different architecture? Why not a different learning mechanism? Okay, and that's where things get interesting. And if at the end of it you do not have a clear answer as to why this paper exists, you might probably be at a better place than you started, because you have now thought about a million research problems or thought about a million research problem statements that might have gone into creating that research paper. Okay, and that's everything that I had that I could share with you. I hope it was good for you. So if you have any questions, you can probably ask me now, or we can meet again later.
Thanks a lot, Ritvik. It was a wonderful session, and the presentation was really visually pleasing, and it was able to understand better with those. And I hope the participants also learned a lot from the session. And there are a few questions that are there. Like one question that is there: how this skip connection help in exploding gradient problem? Does it help?
It doesn't. It doesn't. It helps in vanishing gradient problem. For exploding gradient problem, you kind of need to have a different kind of architecture. But the thing is, if you add epsilon to dl by dw, it will essentially prevent from the gradient to go down. What would prevent it from going up? Okay, would it be something like clipping the gradients? Would it be something like making sure that the gradients are within a certain bound? Search for it.
That's a good assignment. Yeah. And any other questions you can unmute and ask, or put it in the chat. Ritvik will be happy to answer. So I'll also be sharing the speaker's LinkedIn ID. feel free to connect with them over LinkedIn. We'll chat in the group chat. And once again, thanks everyone for joining this session. Hope it was fruitful for you people and joining in a Saturday afternoon, as Ritvik suggested. So thanks a lot. And we'll be conducting more sessions on ML research. ML research. And if you're interested to present some paper, feel free to reach out to us. And once again, thanks a lot, Ritvik, and hope to see you in some other session soon.
Absolutely, my friend. And I just want to say in passing that I've been talking for the last couple of months at various places. The questions you guys asked were some of the most pertinent and good questions I've heard over a long period of time. So you're definitely asking the right questions. That's step one. The step two is actually keep asking those questions and getting to the research literature. So good job, guys, and thanks a lot for having me here.
Thanks. As you said, asking the right questions is the place to start. Is there some other few research papers that you will ask them to follow up with this? Like there was.
Yeah. So as I said, so if you have the recording, please go back to the recording where I am saying what it has evolved into. So those are the names of the papers that you kind of need to follow after ResNet. But really, what you need to follow after ResNet is get into coding something up and then seeing how residuals help you. Okay, and that should be your takeaway assignment. Yeah.
And is there some channels or some places where you suggest to learn, like if like NDAI labs or some other places where you suggest to learn about papers, like some YouTube channels or some vlogs that you would suggest?
Yeah. Okay. Selfish self promotion. I have my own YouTube channel where I do paper breakdowns. I'll probably break down this paper on Monday, but there are a lot of channels. There's 3 Blue 1 Brown, which is great for mathematics. There's Yannick Kilcher, who does a great job about by breaking down papers. But I really suggest you to kind of go ahead and read papers, not see many YouTube videos, not read too many blogs, because when you're doing these things, when you're reading blogs, when you're looking at YouTube videos, what you're seeing is their version of the paper. Even this was my version of the paper, but your version might be more tuned to yourself, to your own understanding. So read papers. Okay, don't rely on crutches like YouTube channels or blogs or tutorials to explain it to you. They might do a great job, but you will not retain that information. You'll only retain it if you extract the information yourself by reading the paper. So go on archive, go on paperswithcode.com, where you will find papers. Read the abstract and see if it makes sense to you, see if it calls to you, and then read the paper. Okay, the first 4 or 5 months might be very confusing, but after that it starts to get better and you start to learn a lot more than by just watching YouTube videos. So yeah,
that's like a good point. Like first get our perspective first, it would be nice. One more thing is, like, people start with abstract. Like, how do you go about reading one particular paper? Do you skim through the complete paper and then reiterate it, or try to understand each part and then move forward? Like, is there some suggestions you would like to give to the audience on that?
Yeah. So if that's something that interests you, what I would suggest you to do is read the paper first. Okay, and it won't make sense in the first go, but in the first go you'll probably understand, okay, some things make sense and something doesn't. So what you need to do is kind of highlight those things as it makes sense and doesn't to you. And after that, at the second pass, you sort of read those highlights, search for them, try to explain them with your own tools, and that will eventually get you better. Start writing the maths on your own, start coding things up. That's how I generally progress. But hey, your way can be totally different and might work for you.
Once again, thanks a lot everyone for joining. Thanks, Ritvik. See you soon. Thank you.
Good. Bye everyone.
Thanks everyone for joining. The recording should be shared in the YouTube channel. Hope to see you all in the future ML paper research club. Okay.